In this video, we're going to discuss exact differential equations and how to solve them. So first we can say that a first-order differential equation is called exact if it can be written in either of these two forms up here, where the partial derivative of the function m with respect to x is equal to the partial derivative of the function n with respect to t. Again, if that happens, then our differential equation is said to be exact. Let's take a little bit of a look here of what's actually going on before we start getting into any examples. So I want to write out that suppose we have some function f of t comma x here. So we have we have a function of two variables here, t and x, is equal to some constant c. So suppose we have that. What would be, if x is a function of t, what is the derivative of f with respect to t? Well, you might recall back in Calculus 3, you did some stuff like this where we talked about the chain rule. So the derivative of this is the partial derivative. Oops, miswrote there. This is the partial derivative of f with respect to t times dt dt plus the partial of f with respect to x times dx dt, which is equal to just the partial of f with respect to t plus the partial of f with respect to x times dx dt, or in other words, x prime. Well, that looks like this expression up here. If m is a function of t and x, and d partial of f with respect to t is a function of t and x, which it will be, then we can get something of the similar form here. So an implicit solution to our differential equation is f of t of x is equal to c, where these conditions are satisfied. So the derivative of, if you take the partial of f with respect to t, that is our function m. And if we take that with respect to x and you get the partial of n with respect to t, then we have an exact equation. Now, we're not always guaranteed that some function like this will exist that satisfies this situation, but we are guaranteed that if this condition right here happens. So let's go ahead and try to solve this. One quick note before we solve this first example. This is just a different form. This is our differential form. So if we see something like that, everything works out just as well. But let's go ahead and solve this. So first example here. Here we notice that m of t comma x is equal to 2tx minus 9t squared, and n of t comma x is equal to 2x plus t squared plus 1. Okay, so the first thing you want to do is just verify that this will be exact, i.e., can we find an antiderivative f of t of x that will solve our differential equation? Well, we will be able to find one if this condition that I just circled is true. So what is the partial of m with respect to x? Well, this is 2t. And what is the partial of n with respect to t? Well, the derivative of 2x is 0, the derivative of t squared is 2t, and the derivative of 1 is 0. So we get 2t. So those are in fact equal, which means we will be able to find a function capital F of t of x. So let's go ahead and do that now. So how do we do that? Well, we want to take the integral of 2tx minus 9t squared. So the integral of the ilm function with respect to t. That was supposed to be a t. And we want to take the integral of n, well, that was 2x plus t squared plus 1, and we want to take that integral with respect to x because of the function that we wrote out earlier. So if we integrate both of these and match everything up, we will find our antiderivative f of t of x. So integrate with respect to t, we get t squared x minus 3t cubed plus some function of x, right? Because if we're integrating with respect to t, then if we derive this with respect to t, this first term becomes 2tx. This second term becomes a negative 9t squared, and the third term goes to 0 because there's no t in there. Now let's integrate 2x plus t squared plus 1 with respect to x. This is x squared plus t squared x plus some function of t, which we'll call h of t. All right, so now let's combine everything. We have a t squared x. So our f of t, and in fact, here's what I'll do. I'll write that out a little bit more clearly. Our f of t comma x is equal to t squared x, and then plus some function of t, so let's write a minus 3t cubed, plus some function of x, which is x squared plus x. And all of this is equal to some constant c as our solution. All right, which we get here. Okay. Let's do a couple more examples. So here in example 2, we get tx squared. Oop. We get tx squared plus 2 minus 3 minus t squared x. X prime is equal to 0, which is tx squared plus 2 plus negative 3 plus t squared x. X prime is equal to 0. So let's take our derivative here. Our derivative with respect to x of this function is 2tx. And the derivative of this function with respect to t, the partial with respect to t, is again 2tx. They equal each other. So in fact, this will be an exact equation. So what does that mean? That means we need to take the partial antiderivative with respect to t on the first equation, on this first expression, and we need to take the partial antiderivative with respect to x for that second one. Okay. So the integral of tx squared plus 2 with respect to t, with respect to t, and then we have the integral of negative 3 plus t squared x with respect to x. Okay. So we get this integral should be 1/2 t squared x squared plus 2t plus some function of x. And then here we get negative 3x plus 1/2 t squared x squared plus some function of t. And so f of t comma x is equal to 1/2 t squared x squared plus 2t minus 3x is equal to c. This should be written correctly on your set of notes down here. I'm sorry, there was a mistake. This should be a negative 3x. But it should be corrected on your handout of notes. Okay. We have two more examples here I want to run through in the video, and actually I am lying a little bit. I have one more example here that I want to run through in this video. And that is this top one, number 3. So we can rewrite this as negative cosine of t plus cosine of x plus x dt plus t minus t sine of x dx is equal to 0. So this tells us ilm is negative cosine of t plus cosine of x plus x, and n is t minus t sine of x. So let's integrate ilm with respect to t. Oh, that was weird. And so that is the integral of negative cosine of x. Oops, sorry, cosine of t plus sine cosine of x plus x dx. Nope, dt. Keep messing up there. What is this equal to? Well, the antiderivative of negative cosine is negative sine of t. The antiderivative of cosine of x with respect to t should be a positive t cosine of x. And then we get plus tx plus some function of x. Okay, so make sure you write that down. And then we're going to do the antiderivative of t minus t sine of x with respect to x. And we get tx plus t cosine of x plus some function h of t. Put all of that together, and we get x times t plus t times cosine x minus sine of t is equal to some constant, c. All right. We have something very similar here in example 4. I will leave that up to y'all to work that one out. And that will end this video here.